Colloquium committee, that's Manuel sitting there. So any good ideas you have for colloquia, which are very broad, scientific, state-of-the-art talks given by outstanding professors like we have here, well, give your suggestions to Manuel, so we're looking forward to have some more colloquia this semester. So then I would like to introduce Professor Maciek Lubczynski. He is from the Netherlands, but as you can hear from the name, not originally. So he's originally from Poland, where he got at least 2 master's degrees in geology, hydrogeology, and civil engineering, and a PhD in numerical modeling in hydrogeology. After that, he worked at the Geological Institute in Poland, and then he moved to the Netherlands, to the International Institute for Geoinformation Science and Earth Observation, IPC, now part of the University of Twente in the Department of Water Resources. It's a very well-known institute in the Netherlands. They have very many international students, and Maciek supervised 50 master students and 9 PhD students, and he's currently also supervising 6 PhD students, but still he took some time out of his very busy schedule to do a 1-month sabbatical with us here. So except for all this professional information, Maciek has been working with us because his daughter worked with the climate group as a research assistant in climate and human health modeling. And then he introduced the water group at Cyprus Institute to SEPFlow, and that's what the Marinos did his PhD on. So Marinos finished his PhD, and Maciek was also an important committee member, advisory committee member of Marinos. So we have already some good cooperation. But Maciek is working in many countries, doing many research projects, and that's what he will be showing to you right now. Maciek, of course.
Thank you very much, Adriana. Welcome everybody. Welcome everybody here, and everybody in the other side of the country or in the other side of the Europe. And I know there are some people watching live streaming even in the other continents. Welcome. First, I would like to thank to Adriana for hosting me during this short sabbatical and inviting me for this presentation. Thank you very much. And I will go right away to the presentation. Well, what I want to say, first I will introduce the threats to water resources. Then I will concentrate on integrated hydrological models, methods of data acquisition for these models, then a little bit on eco-hydrology and the role of trees in hydrology, and finally about conclusions and recommendations. Well, during my talk, pay attention to the red color. There will be some open line research direction that I will notify, so for those who are working with PhD or postdocs, it could be a possible direction of your research. Threats to water resources. There are known 3 types of threats. First is climate change. Second is land use change, and the overuse of water resources. Climate change. Climate change is known to decline the water resources, but not always. So it happens in some cases where the rainfall predicted is more or less stable and temperature is stable, but just the different temporal resolution of rainfall may result of the decline of water resources. Well, we have the study area in Spain that is monitored already for more than 26 years, where the rainfall is, during this 20+ years, is stable and the temperature doesn't indicate much changes, but we notified the change of groundwater outflow and decline of base flow. This is the result of probably different temporal resolution of rainfall, but studies are continued on this topic. Also, land use and land cover change may provide a threat to water resources. Anybody knows the benefits of afforestation, but there are also negative side effects. The afforestation is known to decline water table and river base flow. It can be also declined. In this picture, you can see different areas from China where the afforestation resulted in cumulative water decline. Next case is from Australia, where the clearance of the forest resulted in water rise, whereas the continued forestation will have resulted in water decline. So while reforesting the area, we should remember that it may result in the decline of water resources. Another study from Nepal, where my PhD student Chandra Gimire was doing, he worked on natural forest and degraded pasture and pine forest, and you can see by the numbers how different the results, for example, of evapotranspiration are. So in natural forest converted to degraded pasture, the evapotranspiration declined by more than half and more than 2 times, whereas the pine forest indicated even larger evapotranspiration than in natural forest, mixed forest. So as a result, well, what this contributes to the previous statement that the reforestation results typically, in contrast to former understanding where it was used to assume that forests improve the hydrology and water resources. In contrast to that statement, forest reduces water resources in most of the cases. And the last one threat is the water overuse, so the public water supply, pumping, industrial water supply, and also irrigation, because typically the irrigated water originates from groundwater. So typical association of this process is the decline of water table. As you can see in 4 different studies in the United States, and I have also participated in a study in Poland, where on the left side you have, it is the aquifer, the system of 3 aquifers, and on the left side there is a situation from before installation of the well fields, and on the right side is 30 years after, where the well field is already present, and you can see from the water balance that installation of this well field resulted in the decline of water inflow to the river and the increase of the seepage from the river. So overall decline of the base flow of the rivers. There are in some places in the world, I know the case in Indonesia where reforestation of the catchment resulted in completely disappearance of the base flow. So there was a tremendous problem for people living over there. Integrated models. Well, to handle these threats, there are very good tool to do it is there are integrated models. These models, in contrast to single domain models, they integrate dynamically surface, unsaturated, above surface, surface, unsaturated, and groundwater domains. The main advantages of these models is that they interface the domains, and because of that, the interface fluxes, such as recharge, groundwater evapotranspiration, and groundwater exfiltration, they are calculated and not arbitrarily defined. In the past, well, many people used probably surface water models. And in surface water models, whatever could not be calibrated, it could be adjusted by manipulating the model, and for example, the advantage of water could be attributed as a recharge. And also in groundwater models, the recharge was very often arbitrarily defined. Now, this is impossible in the integrated models, because what is a sink in surface models is a recharge in groundwater models, so they have to fit together. In integrated models, therefore, it's more difficult to calibrate such models, but on the other hand, they are more reliable, and because of that, they are more reliable in their predictions. Well, there are three types of data input. Typical integrated models require spatio-temporal rainfall, spatio-temporal interception, and potential evapotranspiration daily. Then we have parameters of storage and hydraulic conductivity, and there should be some state variables, so calibrated variables that we have to carry on, that we have to use for calibration of the model. The sources of data that we typically use, they are ground-based, so spatial sampling and temporal monitoring at the field, and hydrogeophysics and remote sensing. I will concentrate on remote sensing now. There are lots of remote sensing products from satellites. And why I emphasize products, because products are readily available on the internet. There are remote sensing specialists. They work on processing this remote sensing data, so as, well, some of you are hydrologists, so hydrologists can use this product right away from the internet, offloading from the internet. There are two types of products. There are standard products, standard remote sensing products, and quantitative remote sensing products. Standard are those that we need at the beginning to set up the model. So base maps, digital elevation model, land use, land cover maps, and soil maps. There are various sources. I presented here some of them. More complex are quantitative remote sensing products. So rainfall, interception, potential evapotranspiration, these are those used as the driving forces of the model, and state variables that, well, evapotranspiration, shallow soil moisture, and subsurface storage. I will quickly go through their content. Rainfall is the most important input, driving force of the integrated models. This is my personal photo made in European Space Agency in Noordwijk in Netherlands. This is the picture of the sensor MSG3 that was later launched to space. So you can have an idea how it looks like, the sensor installed on board of the satellite. Let's go back to satellite products. What is interesting and what is important, if you deal with a rainfall product, it is important to know that in different places of the world, different products are optimal. So before you decide for certain product to use in your study, it's good to make an analysis using, of course, ground-based measurements, which product is most suitable in your study area. Well, I haven't done this study for Cyprus, but the two good things that could be applied is one is chirps and the other is MPG. That one is with 5 kilometer resolution and the other is 3 kilometer resolution. Another important thing in processing rainfall is, well, often this rainfall is at 3 kilometer, but you need higher resolution. So that means you need to downscale this product. So there are some techniques, I have no time to talk about it. And also, very often these products are biased, so they are not very correct. So you can do bias correction, and you can use the number of techniques to integrate ground-based measurements with the satellite measurements to improve accuracy of these products. Well, we need for the iGEMs, so for integrated models, we need daily data, and that is a bit of a trouble with data processing. I have some studies. So first study is from my PhD student on Central Kalahari Basin. It's a study where 200,000 square kilometers. This is in this part is in Namibia, and here is Botswana. Well, you can see there was a FISNet offloaded, and the FISNet was used in this study where the 5 kilometer grid in the integrated model was used. Another study was in the Bali Island. It's a bit smaller island than Cyprus, and with much high mountains, going above 3,500 as far as I remember. And it is tropical island. And I found also there is a CHIRPS study in Cyprus. I see it is done mostly, the correction is done for the southern part of the Cyprus, and there is quite some rain gauges, density of rain gauges, so this should be quite a reliable assessment. Okay, that was about rainfall. Well, interception, it's another part contributor to driving forces. Interception could be subtracting from rainfall up to 30%. There are many studies where interception is considered as less relevant, and this is fully not correct. Well, interception, there are three approaches, at least three approaches that I know about. First is, we can call it GIS approach. For that we need land use, land cover map, and we need estimates, rough estimates of interception of certain species. And if we know the spatial contribution of that species to the whole area, and we know the rates using the formula that is presented here, we can make a quick assessment. But this is not top accurate if we don't know the rates, but they are just arbitrarily defined. Another is a remote sensing solution of the GASH model. Below there is a reference, and the scaling interception measurement. This is the remote sensing GASH model global interception after Mirales et al. And and the interception by spatial upscaling is done by my PhD student Hassan. If you are interested, there is a paper reference to it. The method, the principle of the method is to define interception by measurements of truefall and stem flow and the rainfall at different species, and then use very high resolution images. In our case, we used Iconos and Worldview to scale the measurement per species. Another variable is potential evapotranspiration, which is a driving force, and actual evapotranspiration, that is the state variable in integrated models. Both potential and actual, they are much less spatially variable than, for example, rainfall. So, well, if you do the integrated model, if you just offload these data as a product, you very often are okay, because the measurements of, for example, actual evapotranspiration are not very often on the ground. And that this is the example of a global actual interception. Well, soil moisture. Soil moisture can be used also as a state variable, and for many years the soil moisture was restricted to very coarse grids, up to 25 kilometer resolution. Recently, with the introduction of the Sentinel, there is, for some part of Europe at this moment, to my knowledge, there is already C-band soil moisture at 1 kilometer resolution. So, well, if someone is interested, this is available on the web, as far as I know. And there is another one, very nice idea, but not applicable, for example, to Cyprus. This is grace gravity. There are a number of studies, but only in the very large scale, because the pixel of the grace is 400 by 400 kilometer, so definitely not for Cyprus. I'm going to present 3 case studies quickly. First, Central Kalahari Basin, I already mentioned a little bit. Turava Reservoir in Poland, and Sardon Travadillo study in Spain. Central Kalahari Basin, as already mentioned, is a huge basin of 200,000 square kilometers, so about 20 times larger area than Cyprus area. There are 2 papers on that topic, first on conceptual model and the second on numerical model. Here is a picture of the Kalahari. What is important, this structure, it provides water from all the way to the Mahadi ponds. So there is, and very interesting, this basin has a morphology. Despite the groundwater is at a depth of 60 to 100 meters, the groundwater direction pattern follows the topography. About Kalahari, it's highly spatially and temporally variable rainfall area with thick sand cover, more than 60 meters, deep-rooted, thirsty vegetation with various spatial root extension going, by the way, the deepest roots in the world going to more than 60 meters found in the course of the boreholes, and spatially localized, erratic, unpredictable rainfall. So what Lekula did, first he was doing a cross sections to build up the three-dimensional model. He did these cross sections in software. It's kind of subsurface GIS rockworks. Then he evaluated spatial extent of the thickness. There were 6 layers considered. So for each layer he defined the thickness. And then for each of the aquifers, there are 3 aquifers basically. For each aquifer he defined the piezometry. And then he defined conceptual model to be converted into numerical 6-layer model. And this is the grid, which is not spatially continuous over the entire area. The grid of 5 by 5 square kilometers. And this is the result of the model, where water balance with interchanges of the fluxes between the layers and the external inflow and outflows. And this is a result from temporal variability, so daily temporal variability of the fluxes. So you can see in here, the red color is the gross recharge, so the amount of water that reaches the aquifer. You can see the peak, I think it was in 2006, and another peak over here. And then there is pretty constant, lower value, groundwater evapotranspiration. The net recharge is gross recharge minus exfiltration and groundwater evapotranspiration. Because in this area, there is a very thick, unsaturated zone. Groundwater exfiltration was null. So actually is the difference between gross recharge and groundwater evapotranspiration. So the result, net recharge, is printed over here. You can see that every year up to 2006, there is a negative recharge. So the water is lost to vegetation and evaporation from water table. And only from time to time, there is a replenishment, effective replenishment of, well, one may ask, well, how sustainable is this? In this country, the replenishment occurs very seldom. And we know that in 99, 2000, there was a year with nearly 1,000 millimeters of rainfall, and Kalahari was flooded. But unfortunately, we didn't have data to start the model from that year. The confirmation of this, what I was saying, you can see here, this is the whole water balance per year. So you can see that every year the net recharge is negative, and here is the positive, and then the last year is also positive. Highlights. Remote sensing products are particularly suitable as input for large-scale integrated models. For small scale, we still have to wait. The remote sensing products are improved very quickly. So what was impossible, say, 5 years ago, it's now possible, and in another 5 years, even more will be possible. Large thickness of unsaturated zone and thirsty vegetation make Kalahari yearly gross recharge very low and yearly net recharge typically negative. Kalahari groundwater replenishment is decadal and is even multi-decadal. Regional integrated models provide good evaluation of sustainability of water resources at regional scale. If needed, they can be refined into the local scale assessment to study local problems. Another study case, Turawa Reservoir in Poland. This is the study about interaction of the reservoir with groundwater. The difference between reservoir and natural lake is that in reservoir, like in Turawa, within a couple of days, the water, the stage can change by several meters. In case of Turawa, by 5 meters. Whereas in lakes, these changes are very slow. Study area is about 100 square kilometers, and the lake is mean is 13.5, but this area can change depending on the stage of the lake. The system is very complex. There are lots of fluxes playing a role, so this is perfect case to apply integrated hydrological model. This is the grid that was applied, 200 by 200. Well, Al-Zahiri, he did quite some tests, and with 100 by 100, he couldn't run that in personal computer because it was simply too slow. So that was a trade-off of the approach. Well, this is an interesting picture. This line is the stage of the lake level, and notice that the peaks amplitude is about 5 meters, and notice that the peaks of these stages correspond with the maximum and minimum leakages of the lakes, and not...
You can see your numbers.
You can't see them, okay.
On the pointer.
I can use this as an area. So that the peaks of the stages, they correspond with the peaks of the leakages. And the brown is the escape from the lake, and the blue is the inflow to the lake, and the green is the net. What does it mean? It means that in contrast to natural lakes, the artificial lakes, the reservoirs, they are driven by man operation and not by rainfall and evapotranspiration like natural lakes. And this is also interesting. You can see within the lake, the leakages are spatially variable. The yellow is where the water is escaping. The upper one is the low stage, the middle is the medium stage, and the bottom is the high stage. So in the low stage, the majority of the lake the water is inflowing, and the yellow, so the lake out, is just a small fraction. And in the high stage of the lake, the whole area of the lake is losing water towards groundwater. So in some cases, the reservoirs are also considered like artificial recharge supplies. Not in this particular case, because the lake water is highly polluted, but in some other places of the world. Highlights. Well, the Turava study that we have done, to our knowledge, was the first reservoir study ever done by integrated hydrological model, and that solution turned to be optimal for sustainable management of the reservoir and the area adjacent. The man-forced lake levels showed to have much larger impact on groundwater in adjacent area than climatic components. Integrated models can optimally control reservoir-induced recharge, and lake bed lichens and groundwater exfiltration were the most critical components in the integrated model calibration. And what is maybe interesting for you, the two are they are largely understudied in hydrology, so this is a potential field of research. And the third case, Southern Catchment Study Area. Well, this is a semi-arid area, water-limited area, weathered and fractured granite, shallow water table. And what is important, it's a remote area where there is no land use, land cover change, and there is no human impact, because the people are supplied water with a reservoir that is far away from the area. So it is perfect to study the impact of climate change on water resources. And there is 26-year monitoring network in the area. This is how it looks like. So it can be very dry and can be very wet. And in this area, we used remote sensing to locate, very high resolution remote sensing, to locate the outcrops of granite that were outcrops of the second layer. We also used remote sensing to determine fractures and faults by principal component analysis on the images. All is documented in the papers. And we also used remote sensing to scale subflow measurements of the individual trees to determine tree transpiration of the catchment. And also we used the remote sensing to scale the interception measurements that I mentioned already before. And we used also hydrogeophysics. Well, we tried, this is also published, we tried ground penetrating radar to determine the water table depth, but it was not very successful because at the 2-3 meters depth below the ground surface, the signal was disappearing. And then we use electromagnetic methods to define the topsoil thickness. And we used the electrical resistivity tomography to determine hydrostratigraphy, so the layering to fit in the model. And we used also frequency domain electromagnetic, also to determine hydrostratigraphy of the model. Well, and hydrogeophysics can be also quantitative. The only method that is provide quantitative estimates is a magnetic resonance sounding. Unfortunately, it's a very expensive instrument, but it can provide aquifer transmissivity and specific yield. And finally, we have calibrated model, and such model, once it's calibrated, is a powerful tool to handle climate change, land cover change, or water use, abstraction. In this case, we intended to use for the estimates of impact of climate change, as we noticed this trend of the declining groundwater outflow and the base flow. Well, Tanvir Hassan, my PhD student, he analyzed different scenarios of climate change, and he selected RCP 4.5 as the medium, well, hazardous, and the RCP 8.5 as a kind of nightmare scenario, and he analyzed for these two scenarios. He used that calibrated model to extrapolate, to run forward. So first he tested which scenario is the most suitable based on this data that we had, and then he ran forward the model up to 2100, and with the brown line you have this nightmare scenario 8.5 and the more moderate scenario 4.5 in the blue color. So in the upper graph you have the temperature max prediction and temperature minimum prediction, and below you have precipitation. It is very interesting that this moderate scenario did not indicate decline, but slight increase of the rainfall up to 2100. And in the predicted base flow and the groundwater outflow of the area, in all the cases they decline, but the base flow decline much steeper, and of course much steeper for the 8.5 scenario than for the 4.5. Well, how good are these scenarios and predictions? Well, this is another question. And another study, now we go with the scale, we refine the scale, so we selected very small fragment of this model of 80 square kilometer, very small area, with the, so you can see on the northeast side there is a stream, and on the southwest side there is a stream, and in between with the yellow lines you can see water table equipotential lines. So the water is moving from the from this direction towards northwest. So from southeast to northwest. There are, in this study, we did 6 hydrous models. So the idea was to have models on different land cover types. So on the left side there are hydrous models. First on the side A is on the there is a profile under the Quercus ilex, so it's an oak type that is evergreen. The side B is the profile under the Quercus pyrenaica, which is deciduous Quercus, and the side C is an open area where is only temporal grass. And on the right side there are 3 different profiles located outward of the stem of the tree to analyze the impact of the distance from the tree and with respect to root extent. So that was about the hydrous models, and then we have a GS flow model that was done for this area with 5 by 5 meter resolution, so very fine model. You can see on these graphs, this is the result of the model. In the upper left there is a gross recharge, so you can see that from the hilly part towards the valley there is decline of gross recharge, and in contrast groundwater exfiltration on the right side, top right side, you can see that groundwater exfiltration increases towards the valley where the red colors. The same with the groundwater evapotranspiration that increases towards the left side, and the net recharge. The net recharge, you can see that in the lower right corner is the net recharge, where you see the blue colors at the upper part of the of this little catchment, and the yellow and orange colors, so the negative recharge, so the discharge areas on the valley part. So we have classic situation where we have upstream the recharge area and downstream the discharge area. What I would like to emphasize, what was important in this study, is that we had the 2 tree species. One was Quercus ilex and the other Quercus pyrenaica, and you can see this yellowish canopy covers. These are Quercus pyrenaica, and their root extent is documented about the same as the canopy size, whereas Quercus ilex has a with a blue color. So you have in the middle the canopy, and the blue color resembles the root extent. So the quercus ilex has nearly the radius of the root extent is nearly 3 times larger than ground projection of the canopy. So this was actually had an effect on the results that, they are in preparation for publishing. The quercus ilex with the large root extent had, of course, outward the canopy had much larger the water loss. Highlights. Regarding hydrogeophysics, non-invasive water table assessment remains problematic. So we still are relying on the deeper and on the automated loggers for monitoring. Resistivity and electromagnetics is good for hydrostratigraphy, and MRS for subsurface quantitative parameterization. Well, in model, in the shallow water table condition, exfiltration remains important, but as I already mentioned, is the component that requires research, experimental research in the field. Climate change impact on groundwater. Without specific change of rainfall and temperature, groundwater resources decline because of change of temporal pattern of rainfall. That is in the time that we have done measurements. Well, the predictions indicate various results that you could see already on the graphs. And the model scale, regarding model scale refinement with fine grid scale, hydrological differences at different land use, land cover can be well seen. Although different complementary information was obtained from Hydros 1D and from GS-Flow. So we couldn't say one of them was perfect, but the result of the two gave pretty good evaluation of what happened. And the last part of my talk is the tree hydrology. And I will start from evapotranspiration. Well, people talk about evapotranspiration, but in fact is sort of lump parameter, because it consists of physical process of evaporation and plant physiological process of transpiration. More, the two have very different spatial and temporal attribution. So when one is high, the other can be low, and the other way around. So we opt for splitting them. In my group, we always were busy in treating them separately. Well, not always, but most of the time. The process of splitting the two is called partitioning. Very important with regard to that process is the so-called root influence area. So you could see already in this graph that I mentioned that one tree had roots that were restricted to the size of the canopy, whereas the other one was much larger. So if there is much larger this root influence area, then within that area there is a process of transpiration, at least dominant. Well, very interesting contribution to that problem was done here in this institute by Marinos Eliades, who proposed the Voronoi polygons in water balancing of the medium-dense forest of Pinus brutia. There are 2 papers on that topic, so the whole story is described in the same as partitioning, so splitting the transpiration from evaporation, we also claim to be important to split the contribution of unsaturated zone and groundwater. And this process is called sourcing. So sourcing of the tree transpiration into groundwater component and unsaturated component can be done with, by measurement of subflow in the tree and tracing subsequently the xylem of the water flowing in the tree, tracing the unsaturated zone and tracing groundwater. What has been done by Raiz Acosta, another PhD student, he deuterated the groundwater. So he injected deuterated water in the piezometers, and he was extracting the xylem and extracting the soil samples for moisture content. And from the two equations, so this we can estimate by subflow sensors, and these are concentration of the deuterium in water. So from these two sets of equation, he derived the two unknowns, so component of transpiration from groundwater and from unsaturated zone. Well, study is carried out also on sourcing of evaporation. So in bare soil, there is largely underestimated soil evaporation. This is done by Enrico Balugani. He's developed a software called SOURCE to split the observed evaporation into groundwater component of evaporation and the unsaturated component of evaporation. What is important, I don't have much time to speak about this, but in the past scientists usually considered capillary flow as a main process of evaporation from subsurface. In very dry conditions, so in Drylands, after a number of very dry days, there is developed so-called dry soil layer and vaporization plane, and water is moving by capillary forces up to the vaporization plane and then goes by vapor to the surface. Enrico is working on this process. Further, he did some columnar study in Wageningen, and he has also lysimeter in the field, so there are some more studies than this presented here upcoming. There is also another study we have done that's also with Balugani, where we used the eddy covariance tower, and we had measurements of the subflow of the trees, and the idea was, in this study, also published, that we wanted to compare the evapotranspiration from the eddy covariance tower with the sum of the subflow measurements and the evaporation estimated from profiles of soil moisture. Well, the results are presented. In one period, the result was pretty good. In the other period, not. There is an extensive discussion on the reasons of why in this study there were some disagreements between this ET and some of the T and E. Well, the difficulty, one of the main difficulty was the the changing, continuously changing the footprint of the